I'm very happy that I can sort of give the introductory talk today. Johannes gave me a job to do here, basically, when he asked me to do this, to give a brief, mostly layman's overview. So I've tried to put a couple of slides together to get us into the topic. Whenever you have questions, even in the middle of the talk, because what I said wasn't clear to you, or you'd actually like to go a little bit deeper, I think we can probably do that. So just use the raise your hand feature. We can do it after the talk anyways. It shouldn't be too long, I think, what I've prepared today. And again, I try to give a big overview. It's less of my personal research here. I'm a little bit fish out of water in a philosophy workshop, if I'm honest. So I'm very interested to see what comes out of it at the end. Yeah, open to any questions during the middle. So I titled the two big things here, I think, in the title. Does the hardware matter? For someone who's interested in at least being a collaborator in building neuromorphic hardware, so literally new devices. That's a quite existential question, of course, right? Because if it doesn't, what are we doing? And the second one is a surprisingly existential question as well in the neuromorphic computing world. What's a neuromorphic computer anyways? Because the definition has been changing and shifting over the last 20, 30 years all the time, and more so recently together with a big AI boom. So we are going to try to keep that in mind as we go through the talk. Just to kick us off, the two big comparisons that people usually make when they talk about either neuromorphic computers or traditional computers are that traditional computers are identified with what's called von-Neumann architectures. The definition is a little bit too broad, but it fits roughly, right? So it all goes back to some of the computer science work that John von Neumann did in the 50s. Here he is at Princeton in 1952 about. And I'll tell you a little bit more about what that means. And the other big sort of important person or persons from the other side of the equation, the neuromorphic side of the equation, i.e., let's build computers that work like the brain, Carver Mead and his PhD student Misha Marwold. Here, picture. I didn't find an exact date for the picture, but I'm pretty sure it must be late 80s at Caltech, where it all started sort of together with in a seminar together with Dick Feynman and John Hopfield, where they sort of Carver Mead really came from the electronic side of the equation, where they started to merge all these ideas together and start building circuits that they wanted to work like the brain does and compute sensible things. So I don't think that helps yet, right? So what's a von-Neumann computer really? And in terms of applications, it's very easy to see that the application range is extremely broad, right? Everything from like the first supercomputer, that's the Clay computer here from the late 50s, I think, to the IBM personal computers, to the first laptops, in this case the PowerBook, to mobiles, to face computers, to wrist computers, everything. Every chip in there is essentially what we could call a von Neumann computer. In terms of the actual computing devices, at least for the purposes of this talk, I'm including microcontrollers as well, CPUs, the standard stuff that powers all our laptops, and then the more specialized chips as well, GPUs that power the modern iteration of deep learning and artificial intelligence, as well as more specialized chips like FPGAs and others. You don't have to talk really care about the details, but there's a wide variety here of different computing devices that fundamentally operate in similar architectures, at least in parts, right? And they power the entire digital revolution essentially. Whereas on the neuromorphic side, we have a much sort of narrower view of what the application is, because we really want to go towards artificial intelligence, but in the field generally, really towards sort of autonomous intelligent systems, because we want to sort of replicate what the brain is able to do, which is to autonomously understand the world and make intelligent decisions in it. So you'll more often see applications. For example, this is the hand of Elisabetta Kika from Groningen and her PhD student. They're building a robot here to work on insect, to test how insect vision works for navigation, right? So they're putting the robot with the neuromorphic system into the real world and have it behave autonomously. And this picture on the right-hand side is from a recent publication where the neuromorphic system controls everything in the drone, basically, right? So the flying, the perception, everything from input to output, right? And that's the type of system that neuromorphs are most interested in the application, right? And I think Chiara Bartolozzi's keynote will go much more into detail here. But then, on the other hand, compared to, I mean, we do have some diversity of devices here, but they're all products, right? On the neuromorphic side, the computing devices here, I mean, there are a couple of companies are involved here, right? So IBM and around 2014, this is a picture of the True North system. So the individual things here would have been underneath would have been True North chips. And then more recently, the Intel UE2 system. Those are made by research labs and big companies, but we also have, for example, the Braindrop chip, complete research chip, right? Completely different architecture. Not many commonalities between these two. Memristive arrays, so that's a completely different thing. The picture doesn't tell you anything. I'll tell you a little bit about what it does later on, but not in detail. Complete research stage, even on a smaller scale than any of this stuff. Brain Scales is a system in Heidelberg, all research, right? Huge experimental stuff. And then there are some products as well that combine, for example, in Synsense products here, the Zylo chip on the left-hand side and the spec chip with a camera. That's more obvious that this thing has a camera involved. They already include some of the sensing together with the computing device, which already tells you that this is this robots, drones, autonomous agent stuff is what many people in the community are interested in solving, right? But comparatively, this on the left-hand side, you can see computing devices with mature technology, and on the right-hand side, a wide diversity of computing devices with sometimes very few commonalities, almost all at research stages, right? Very few products. Where on the computing device stage, on the von Neumann architecture, of course, everything's a product here, right? This is where big money is made, right? Sort of the way to distinguish the two applications here is sort of in terms of artificial intelligence, and then maybe AGI or anything that might follow from there, is on the von Neumann side. AI is always sort of part of the application, right? I can build software that acts as an AI agent and put it on your phone, on your wristwatch, on a supercomputer, on a desktop computer, but it's part of the system, right? Whereas, and one of the things the system can do. Whereas for most neuromorphic applications, AI, the artificial intelligence thing or the autonomous intelligence thing, really is the application, right? And then I already said on the left-hand side, you have mature products, on the right-hand side, you have diverse research. And it's really, I think, even in the context of the philosophy of these devices, I'm assuming at least, it's important to see that on the left-hand side, it's quite clearly defined what you're talking about, and then the right-hand side, it isn't. Right? Okay, so I wanted to give a little bit of sort of context what the von Neumann computer actually does to then say what's different in the neuromorphic computer. So the standard procedure, if you want to solve a problem with a von Neumann computer, is you write a specific program that solves that program, and the entire von Neumann machine, the CPU in this case, is built to execute all these instructions you put into your program specification sequentially, and then it will give you the answer that you specified. Right? If it's the wrong answer, you specified something incorrectly. Right? So you receive the answer that you've encoded. So you give a detailed list of instruction to some kind of computing machine type factory type thing, and out comes the product, right? In this case, I put a blender here, but of course, software products are cheaper, right? So all kinds of software products come out of this, right? APIs that you can query on the internet, or the couple of sentences of the answer that ChatGPT will give you if you give it a query. Right. The important thing to note, though, is that this computing machine in the middle, of course, is attached to a very successful theory that predates the machine, right? This is the Turing machine that Alan Turing invented just after, like, even before he started the Second World War. And the real, almost frustrating thing for someone who wants to build a new computer is that this Turing machine basically, I mean, there are computation classes that are outside of the Turing machine. But to say that your problem isn't part of the Turing machine sort of class of problems that you could at least in theory solve, you have a job to do, right? So the Turing machine is really, really quite powerful, and it's general. It is a huge advantage. And I'll get back to that later on. So here are a couple of architectural details for the von Neumann machine, the actual implementation of the Turing machine. This is the picture that you find on Wikipedia and in all kinds of places, right? So it's I'm calling this a separation of concerns architecture, right? So different things are in different places on the machine, right? The most important things are in the middle here, right? So let's talk about them a little bit. In your CPU, your central processing unit, you have a control unit. In the previous picture where you're giving the thing a set of instructions, this control unit will be responsible for fetching these instructions one after the other, right? Get the instruction in, make sure that the second unit, the ALU or arithmetic logic unit, executes whatever you put on that piece of instructions. And in reality, it will be as simple as this is a number, please add them together, give me the result. Right? That will be the instruction. In reality, it will fall down into more micro instructions, but that's not important. That's the thing that the control unit fetches. I'll tell you where from in a second. The arithmetic logic unit will compute the actual result, and it will store the result somewhere else. All the programs, all the data, and all the results are stored somewhere entirely different, right? This down here in the memory unit. On the computer, this goes from when you read CPU spec sheets, right? That might be your cache. It's the RAM that you put into your computer. And at the end of the day, it's your hard drive, right? Where you store your program and you store the data to compute from it. Your control unit will start fetching stuff from memory, start using the instructions. It will also fetch data. It will put these into the arithmetic logic unit, which will then execute, and then you get return. I think a useful way of thinking about this is your control unit is sort of middle management, right? You're the CEO, you tell the company what to do. Middle management figures out who's actually going to do what at what time. And you have all your specialized worker, and in this case, they can be highly specialized, right? They only know how to add two numbers, 8-bit integer numbers, for example, if that's important. They will do the execution, and then you have the warehouse where you sort of get the data from, and you have your post box where all the instructions come in and where you store your result, and that will be shipped off to the user later on, right? This is sort of the von-Neumann approach to doing computation. And in the brain, where just neuromorphic is, of course, the idea to compute like the brain, none of these separations really exist. So there is no instruction, there's no ALU that's separated from anything, and memory and compute is always at the same space. It has to be, right? Because we don't have, at least in the local computational unit, there are areas of the brain which are more focused on memory type things. But generally speaking, in terms of the computation, you have to have all the information locally, physically at the same spot, otherwise it doesn't work. Right. And this is the way you can sort of think of it entirely different from a very high level perspective. The neuromorphic system, of course, is here. I'm boldly claiming this is at least somewhat similar to a brain. Works usually in an environment from which you sense data. You might already have a data set and you're more in this modern AI world. All this data goes into your neuromorphic system and you produce some behavior which will have an effect on the environment. And then there's probably a learning loop involved here, right? So the problem is really defined in what you want to have happen in the environment, but you find a way to specify that. In machine learning, this is the loss function, right? The error, or some reward function that you put to the system, right? If you achieve this type of behavior, I'm going to reward you, and you figure out how it's done, right? And the system is responsible for figuring out how it's done, right? Get all the data, get all the experience from either interacting or from just a huge data set, and you figure out how to adapt so that the problem actually solves. That's the quote-unquote programming model in the neuromorphic sense, right? Which is completely different than anything in this sort of instruction-driven way. Right. It's important to say that the way I framed it here is the way all machine learning problems are framed. Right? So this is not unique to only neuromorphic, but you cannot frame a neuromorphic problem easily in the way in a set of instructions to a computer, whereas a machine learning program, whereas a computer that you can run on a normal, that can run your machine learning problem and solve it for you, can do all of these other things as well. So from the computation point of view, I think this is important to distinguish that we are more narrow here. Right. And then the big sort of spanner in the works is, of course, well, Turing machines can do, for example, machine learning. So why would you need in simulation? Why would you need any specialized hardware at all, right? What's different about a neuromorphic computer as a physical device that might make a difference here? I actually don't have a definite answer to that. I'm just going to talk about a couple of points that I think are interesting to consider, and the real answer is probably 20 years in the future. We'll see. Right. So the first thing to do is, and I don't exactly know what Herbert is going to talk about later, but I suspect he will talk a lot about this point. Right. So in neuromorphic computation, we often don't want to do simulation, right? But we want to use what people call device physics. right? So instead of calculating, getting the formula to calculate, for example, a sinusoid, we'd rather have a material that if we excite it with a little bit of electrical current, it automatically produces sinusoidal currents or voltages for us. And then we use that for some kind of computation, right? Because that's usually much more efficient. We don't want the simulation, we want the real thing. The easiest way to think about this is instead of doing digital electronics, like our computers does, right? We encode everything in 8-bit, which is an approximation of in terms of floating point numbers, which will always be approximations. We do calculations on that, get a simulation, try to find a way to encode dynamics in an analog circuit, and do computations that way. That's sort of the traditional neuromorphic way to do this. There are a bunch of reasons people do it this way. Energy efficiency can be a point, but fundamentally, the difference is that we want to set up a device that automatically has the dynamics that we want for computation. For example, exactly the dynamics of the membrane of the neuron in the brain, right? Which this is an example if you don't care about the details. The extreme version of that is brain scales. This is the newest version of them of it. This is a product from a project rather from Heidelberg, from the neuromorphic center there. And this is a really complicated system because they do these analog circuits at a huge scale, right? So they really have lots of them, and they try to put thousands of neurons that all run in terms of where the electronics run the dynamics that you would see in a neuron in the brain. Try to emulate it basically as close as you can. But you don't have to stick to that. You can also do a mixture architecture. This is BrainDrop. I showed this earlier. This is a project led by Stanford by Corinna Bohen there, was published in 2018. So here, this part of the circuit here are these analog circuits, right? So where you are building with electronics, you're building devices that have the right dynamics that you want instead of doing the simulation. But they only do that for some of it, and for the rest of it, all the rest of it around here, right? So this M part here, the C, D, G, F, Sps, these are all more standard traditional digital electronics, where you're encoding, where you're working with a clock, where you're not using the dynamics of the system, but you're really defining a digital computer that does the rest for you, basically. This, for example, here is a huge memory array. So this is in a similar way that von-Neumann separated memory from computation. The memory is separated from the computation here, but they're combining the two approaches. And then, sort of on the more out there side, what you can also find in neuromorphic worlds is these memristive crossbars here. Memristors are de facto just another element that you could put. We have an example later on for a resistor in the circuit. There is none here, but as a circuit element here, which is new device physics, right? So it's a new dynamical element. It behaves differently than other ones. You can't really use it that easily in a digital computer, but you can make use of it in a neuromorphic computer. The way it changes the dynamics of the electronic circuit, and I'll show that in a second. The more crazy stuff out there also completely abandons the idea of doing this in electronics altogether. And for example, people set up dynamical systems with lasers, so optical systems, where there's an LED here that sends light through this complicated long wire with a loop, and there's complicated dynamics happening here. And just from these dynamics, people are trying to figure out how to do computation. This is a couple of steps removed from we do computation like the brain, but it's very much in the sense of I built a device with the dynamics that does the computation for me without me having to do the simulation. So this is sort of, for some, this isn't really neuromorphic anymore. Others disagree, right? I think it's at the very least on the boundary. The funnest example I think of this is a sort of Lego adorned water basin from 2003. This is literally a bucket of water, and the input, right, which you'd usually have for example, from your memory, the input to the system is these little Lego motors here will move things up and down, and there will be water patterns in the water, and these patterns that emerge can be used for computation. So dynamic behavior of real systems you can already use for computation, and this is something that neuromorphs like to make use of, right? To get out of the simulation paradigm and into the no, let's just build the system and have it evolve naturally. Right. But really, so especially from the perspective of what modern AI is all about, neural networks, right? The next two things are, I think, a little bit more, at least as important, let's put it like that, right? I said in the beginning, these von-Neumann architectures are fundamentally sequential processes of information. The reality, of course, is that they don't limit themselves to it. They build more complicated machines that they know how to parallelize. But fundamentally, the brain is completely parallel. Everyone talks to everyone they are connected to ad nauseum, completely asynchronously, all the time, and the brain figures out how to do computation in that situation. And it turns out that can have huge advantages in terms of scaling the number of neurons you can put in the system and how you can send information around and stuff like that. Right. So really, these two systems here, the True North system from the mid tens and newer the Louis system, they're really fundamentally digital chips. So they work fundamentally still like a digital technology, like a von-Neumann computer would as well, but they optimize for parallel and distributed computation. So they have lots of little small cores that can simulate a couple of neurons, and then they focus on the task of how do I make many of them work in parallel and be able to and make them able to communicate with. So this is sort of the next point with spikes, right? Um, uh, and then to go back to this point here, the one point I did want to mention here, of course, from the other perspective, the ANN von Neumann machine optimized for parallelism, right? This is what people are also doing. Right? GraphCore is a British startup which released their product in 2021, this GraphCore IPU thing, which is fundamentally a highly parallel von Neumann computer. And NVIDIA GPUs are fundamentally also that. And they run the current generation of AI. Right? So the lines here are a little bit blurry, at least on the parallel distributed computation part. Lots of things happening at the same time, lots of computation instead of sequentially. And that's because the models that we use, the software models, already lend themselves to this, of course, because they're also modeled after the brain. Right? So the simulation is more efficient if the hardware also makes use of that. So that's sort of the boundary here is not clear. But this computation with spikes is also, for example, present on these two products here, and they really take it quite seriously. So they will have some analog neurons on there as well that will only communicate with spikes just as the brain does. And for many, that includes, I think, to a large degree, I would include myself in that group, that you do computation with these spikes, and I just noticed I should have said what a spike is. So a spike really being the nerve signal that one neuron sends to another, right? It's a precise point in time when neuron A tells neuron B a spike, and that's all the information neuron B gets. That's it. And instead of the model where neuron A tells neuron B 0.75895678, that's much more information in theory, right? But you also need a different channel to communicate the type of information, right? For example, you need a bit encoding or something like that. The spike is super simple, but it also doesn't carry a lot of information on its own, right? So figuring out how to make this spike carry a lot of information and use that spike in computation correctly is actually a huge challenge in the neuromorphic world, right? But if we can do that, we can also make use of a bunch of hardware sort of tricks and to make the hardware more efficient if we use these spikes. Next point, of course, that we're really on about is that we want our system to be ideally inherently adaptive, right? Like our brain is adaptive to internal changes as well as external changes, i.e., learning from the real world all the time. Right? That's usually covered under the term plasticity on many, many different scales in the brain and acting on many different systems. And many of the bigger chips don't explicitly include that or basically have that as an external configuration, right? I put the system on the chip in the neuromorphic world, right? I put the system on, I see how it behaves, and then I have some way of measuring how it behaves, and I outside of the system figure out how I want to change the system, and then update the system afterwards, right? I could do that. But the newer way, for example, this is from Milika Paivan from Zurich. It's relatively new. This is a circuit now that is self-adapting, right? So there's a learning rule that we know from brain science, it's called SCDP, that she implemented here in the device. So the device dynamics, similar to point one here again, right? The device dynamics are now taking care of this adaptation automatically, right? And the way she does it is with this new device called the memristor. This is these RT components here that you can see here. These are these memristors, so they act as a resistor, i.e. they slow the flow of current, or they attenuate the flow of current through it. But the amount to which they attenuate, you can sort of either as a user or the system can itself set how the resistance value of that, right? So that will change the dynamics of the entire system, and in this case, they are changing what you would call in the deep learning world the synaptic weight, right? So we're building systems now that can really inherently adapt already. The other point that I don't know any neuromorphic system that's really included this yet is the huge heterogeneity of the system that we're looking at, i.e. the brain, right? The variety of neurons, types, structures, and very specific area configurations that we have in the brain, for which fundamentally, this is the point I will come to later, we don't have a good theory for. So we usually try to ignore them when we build them. They would actually be a huge burden on the engineer building the system. So we're just ignoring them for now because we don't know what they do, right? But fundamentally, this heterogeneity of the system components is probably, I suspect, also an important part of building neuromorphic hardware that excels, right? And then lastly, this is the embodiment point, right? We usually don't try to build systems in isolation because we are not in the situation that we can simply write a program and then expect the chip to execute that program. So there's lots of people thinking very actively about the embodiment of the system in the real world, and this is really Kiara is at the forefront of that. So looking forward to what she has to say about it. Where the neuromorphic system is really, so there's a person here, the neuromorphic system is sort of controlling the robot, is getting lots of vision input, right? So lots of sensory input. They are working on this sort of interesting neuromorphic touch sensors here, right? So there's a touch input as well. And of course, the robot can act in the world as well, right? So it's as part of the environment. And Lila Better does some work like that as well, and Groningen, which really I think should be seen as part of the system. Okay. The problem though is, and at each level, before I get to the problem, sort of and I say opportunity here on the slides because I really don't know, and I wouldn't believe anyone who claims differently. The opportunities that there are sort of really necessary ingredients at each, like either on the level of the dynamics that we get, on the level of parallelism and distributedness, how we are dealing with spikes, how we are adapting, how heterogeneous the system is. At each of these levels, there are opportunities for necessary ingredients that you would need for a system that goes beyond current AI, right? Towards cognition, towards AGI. I wouldn't make any claims as to how far you could get on that scale. Possibly at each of these levels, you'd need an ingredient for specific capabilities of the system to be able to emerge in the first place, right? This is a relatively open hypothesis that I think is actually not too controversial because it's so open. But that means that we have to really, what we do when we do neuromorphic computing as a sort of theoretical science, we really wonder about what it is on each of these levels that can contribute something to the computation from the dynamics, from the sort of communication within the network parallelly with spikes, from the adaptation that goes beyond what was there sort of in the first place just from the system description. Right? And that's also the chance when you're morphic, where you would then have the chance to go beyond simulation. The problem, of course, is that to each of these levels is also, especially to the first five in terms of the brain, there's a huge level of biological complexity attached to it, for which we have no good methods to reduce it. Relatively good models of how we generate these spikes, this communication protocol from one unit to another, but that's about it from where I'm sitting, right? We know how these are generated, we know a bunch of things that are involved, and we know lots of things that are happening in the brain, but we don't know how to generalize over them in a fashion that we are not losing something that was essential to what we're interested in, right? For example, intelligent behavior. And in principle, all of these you can still do in simulation. There's nothing stopping you from writing a computer program that where you're simulating the dynamics, you're parallelizing, you're writing the system as if it were parallel, even if some of it will be computed sequentially later on. You're using all these amazing chips that are available now. You can, of course, also send spikes. You might use 8 bits to represent a single spike on your actual CPU, but whatever, right? You can simulate it. And plasticity is actually much easier if you can control it in your simulation. All of these are no fundamental issues for you that sort of prevent you from doing this in simulation. However, what I think is the key ingredient here is I don't think you can do it at the scale that's required. And I think this might actually be true for every one of these levels. So I think you could certainly build a device that simulates 1 to 2 or 3, a small set of neurons with a required complexity on the level of dynamics, right? The actual device dynamics that is required in the big system to get all the features that you want out of it. But I think you run into trouble if you scale that up to 1 million, right? And that's the sort of, if you want to compare to the brain, in the brain, everything scaled to the nth degree, right? And we're not even close to that. The same is true for communication. Even the IBM True North chip, for example, that and the Intel Louis chip, they all have specialized protocols that are relatively efficient at sending spikes around from A to B. But in principle, the type of connectivity that the brain supports is really, really difficult, especially like on a 2D chip, right? 2D simply means you're still working on a plane. Your cables connecting one part of the chip to another might come out of that plane a little bit and then move to another bit, right? But you're basically doing these types of connections literally on your chip. They're literally there, the connections, right? And if you have to connect 10,000 inputs to each individual neurons, there's not enough space for your wires. That's just technologically, that's not possible in any of the standard current technologies, right? Whereas the brain, of course, is a biological system. It's 3D. It isolates its wires from each other in a different way. Right? There are lots of things that are in theory possible there in terms of scale. It's the same for all the other components. And if you need just a little bit more sort of scale at each of these levels to be able to achieve sort of higher levels of cognition, if that's the case, then I think neuromorphic has potentially the chance to really set itself apart from traditional AI approaches, because you're leaving the domain where simulation can cover this. Right? The simulating computer will, at the very least, you have the trade-off of, if you want to simulate this with a computer, the computer is now suddenly a supercomputer connected via the internet, and then you're losing embodiment probably, right? So then you're in the sort of a trade-off domain where I think neuromorphic really does make a difference. Right. A very short summary on the technology bits, right? New technologies are still developing on all of these areas, right? We're building new stuff, hardware is improving. But that's the sort of other hidden truth. We usually want to build spiking neural networks in these devices. If I'm going to train a spiking neural network today to solve, for example, an object I want to show with pictures, and it is supposed to recognize objects in there, it will do a significantly worse job than if I just did a deep learning system, a relatively simple one probably, using standard modern AI architecture. And that's because our theory of computation, spiking neural networks in the brain, doesn't fit one-to-one to what ANNs do, to what deep learning does. Deep learning is just an optimization problem, and the spiking neural network usually isn't. Plus, the spiking neural network is a more difficult optimization problem. So we're really lagging behind in all the AI applications that you would see today, right? If you do that with an SNN, you're probably worse. There's a high likelihood, and you might even be so much worse that you can't even get close, right? When you're talking about large language models, for example. So what's really needed here is developments in theoretical neuroscience. That's sort of my field of research. What I'm trying to push to also make the case of what complexity is really required in the system, get it from that direction, and push SNNs to be much better than they are today. Because otherwise, the hardware sort of research program and neuromorphic can do the best job in the world if we can't put the right model into the hardware at that point. Right? We didn't win anything. Right. So I started with the question: does the hardware then actually matter? Right. So first of all, the first step that I mentioned on the last slide is, well, first of all, you need the model to make the hardware better. Right. You can't just build any hardware and expect it to work. I don't think that's a recipe for success. If you do that, my hunch is that what really matters is the scale and the scale of complexity. Right. And so if you were to look at the scale like that, right, where you're furthest away from the brain and then you're getting closer to the brain with GPUs, here you have more parallelism, but it's really just a standard von-Neumann computer. Then you work moving over to Luigi, where you're kind of using von-Neumann type architecture paradigms, but you're really building a spiking system now, all the way up to the brain. And from this perspective, the question really is, sort of can neuromorphic hardware achieve scale and complexity that you cannot achieve with traditional hardware? Is that, and that I think so, sort of from current technology, there's no yes or no answer here. I don't know. But this barrier would be important from this perspective, right? So then there would be qualitative difference if you move beyond this line here, right? You can do some. You could expect that there's something you cannot do here, but that you can do here, right? And the second boundary is, can it achieve a sufficient amount of scale and complexity to get close enough to the brain? Which I also think is an unanswered question, because we're still building electronics here, right? This wiring problem doesn't suddenly go away just because we're doing neuromorphic more. It becomes way more important, and we might have more ideas of how to solve it compared to this world here. But if a certain amount of scale is really important for systems to achieve something similar to what our brain does, then there might be a second barrier here that doesn't, at least with technology approaches that exist right now, doesn't allow us to move past this right here. And with that, I basically mean all of electronics, right? It's not like, some new electronics will come along and then it will work. No, there might literally be a hard boundary here where it needs to be a completely new class of, we manage to somehow control, like grow a brain in a jar, basically. Which at that point, I'm pretty sure we're giving up all kinds of control, and I'm not even sure what we're doing then. I think it's difficult to call that neuromorphic hardware then. So these two boundaries, I think, really fundamentally important to answer the question, does the hardware matter? And I don't know the answers. Interesting to see sort of what you will be talking about throughout the workshop today. And that's me done. Thank you.